Welcome back to the Deep Dive. Today we're tackling system architecture, specifically for really scalable systems.
That's right.
We're zeroing in on a pattern, command query responsibility segregation. That sounds, well, pretty complex.
It does have a bit of a mouthful of a name.
But one source actually boiled it down to one diagram and 178 words. So our goal today is to unpack that concept, CQRS, and give you the context you need.
Absolutely. We're diving into CQRS if you're building modern apps, things that need to handle, massive load, scale well. This pattern is pretty foundational.
Okay.
At its core, CQRS is really about optimizing performance, responsiveness. It tackles this fundamental conflict.
Conflict.
Yeah, the needs of reading data versus the needs of writing data. They're often completely different, almost opposite.
So the name CQRS, command query responsibility segregation.
Right.
It literally describes what it does, splitting responsibility.
Exactly. It's about physically separating those two key functions. You have commands, which change the system state.
Right, the right side.
And queries, which just retrieve information, read-only.
And that separation is the shortcut to optimizing performance.
That split is everything. Look, for simple apps, one database, one model, totally fine. Works great.
Sure.
But when you hit a certain scale, maybe your read traffic is huge, like 100 times your write traffic.
Wow.
Trying to force those different operations optimized for opposite things through the same shared resources, that becomes a huge bottleneck.
Okay, right. Let's unpack the terms then for anyone maybe less familiar. Commands and queries. What are their specific jobs here in CQRS?
Okay, so we divide the instructions into two clear types. Commands are explicit instructions to change the state.
Create, update, delete. The CUD part of CRU.
Exactly. And they're always transactional. They have to pass business validation rules. It's all about intent and, crucially, data integrity.
Got it. Intent and integrity for commands and queries.
Queries are purely passive. They just retrieve information. They don't alter anything.
Read-only.
Totally read-only. And the key architectural point here, because we've segregated them, each side can have its own completely separate optimized data model.
Oh, interesting.
And potentially even its own dedicated storage technology. Different databases, maybe.
So we're not just splitting the application code logic. We could be splitting the actual underlying data structure itself.
Precisely. That's the real power. You're no longer tied to that single, often heavily normalized relational model that you need for enforcing right-side integrity.
Okay, that brings up the strategic question, though, this separation.
Yeah.
It sounds like it adds complexity, right?
It does.
Managing two models, maybe two data stores, keeping them in sync. When does that overhead, that complexity, actually start paying off? Are we just trading one kind of complexity for another?
That's the crucial calculation you have to make. CQRS isn't free, it's an investment. And it's generally worth it under two main conditions. First, when reads and writes have dramatically different scaling requirements.
Like that 100-to-1 read-write ratio example.
Wow. Exactly. And second, when the requirements for the read model are fundamentally different from the write model's needs.
Okay, tell me more about those different requirements. Why would the read model need to be so different?
Well, the write model, the command side, it has to be almost obsessive about enforcing business rules, ensuring consistency, validation.
Right, the integrity part again.
Exactly. But the read model, it doesn't enforce anything. Its only job is to serve data to the user, like instantly.
Oh, okay.
And this lets us to do something called denormalization.
Denormalization. Okay, let's dig into that because that feels like a key architectural shift. It sounds counterintuitive, like making data messier.
It does sound a bit wrong, doesn't it? But you're doing it strategically, purely for performance.
How so?
Think about a traditional system. To show a product page, you might need to join data from, 7 different tables.
Yeah.
Product details, inventory, pricing, reviews, recommendations.
Yeah, those joins can get complex and slow.
They really can. With CQRS, the read model is often denormalized. We essentially pre-calculate or flatten all that information needed for a specific view.
Pre-joining it almost.
Sort of, yeah. Into a single structure optimized for that one query. Maybe it's a single JSON document in a document database, or just a flat row in a simple table.
So instead of a complex multi-step join at query time, you're doing a single, super fast lookup of a pre-built view.
Exactly. You're replacing a potentially slow query with an immediate fetch. It completely changes the performance characteristics for reads.
That makes sense. Performance is the priority for reads.
Absolutely. The read models prioritize speed. They might sacrifice some storage efficiency or even immediate consistency because the right model is still the guardian of the actual truth and integrity.
Okay.
And that's the scaling advantage. We can throw, say, 10 times the server resources at the read models to handle massive user traffic.
Without impacting the right model.
Exactly, without compromising the right model, which needs to focus on those critical, consistent transactions.
Understood. So right model enforces truth. Read model displays it, maybe with a slight delay. Okay, if the data is split and the command side is the source of truth, how does the query side know what the latest truth is? How do they stay coordinated?
Coordination. That's the critical piece that makes CQRS work as a cohesive system, not just two separate databases.
Right.
And this is where CQRS is very often used alongside another pattern, event sourcing.
Event sourcing. Okay, that's a big topic in itself.
It is. It's a significant architectural decision.
Before we dive deeper, what does event sourcing mean in this context? What are we actually storing?
Okay, so with event sourcing, the system state isn't stored as the current value of data. Instead, it's stored as a sequence of immutable, time-stamped events.
Events, like actions that happened.
Exactly. Think of it like an accounting ledger or maybe a continuous log file. When a command gets executed successfully, say, change shipping addresses, the right side doesn't just overwrite the address in a user table. It records a new event. Shipping address changed. Timestamp, user ID, new address details. This stream of events becomes the single authoritative source of truth.
Wow. So you're recording the history of changes, not just the final result. That sounds incredibly useful for things like auditing.
It's fantastic for auditing, yes, but it enables other things too. One, like you said, perfect audit log. Two, you can theoretically rebuild the system state at any point in the past by replaying events up to that time, like time travel for your data.
Oh.
And three, crucially for CQRS, these events that are generated by the right side, they get published. And other parts of the system listen for these events to asynchronously update the read models.
Okay, asynchronously. That feels like the key word there, and maybe where the complexity comes in.
It is?
If the write model commits an event instantly, but the read model only updates later when it processes that event, there's a delay, latency.
That's right. And this leads us directly to the concept of eventual consistency.
Eventual consistency. We can't just gloss over that, can we?
Definitely not. It's the primary operational trade-off you make with this style of CQRS. You gain potentially massive performance and scalability.
But you lose.
You lose immediate consistency across the whole system. Eventual consistency means the system will become consistent over time, but there's a window. Could be milliseconds, could be seconds, where a user might write data, immediately query it back, and see the old value for a moment.
What does that mean for the user experience practically? If I update my email address and hit refresh, I might see the old one for a second or two.
You might, yeah. And architects have to explicitly design for this. Well, sometimes for critical updates, you might redirect the user immediately after the write action to a specific page that forces a direct lookup against the right model, the source of truth, just for that one piece of data.
Okay, a temporary workaround for consistency.
Kind of. Other times you just accept the small latency because the overall performance gain across the system is so valuable. Think about, say, e-commerce inventory counts. Seeing a stock level that's a second or two out of date is usually acceptable as long as the actual purchase transaction itself is perfectly consistent against the right model when it happens.
Okay, that makes the trade-off clear. It depends on the specific use case. So managing this event stream, the asynchronous updates, that sounds like it needs specialized tools.
It often does, yes.
What kind of technologies did our sources mention? Things purpose-built for this.
Because CQRS, especially with event sourcing, is a specific pattern, developers often reach for frameworks or toolkits designed for it. In the Java world, for example, the Axon framework is a prominent one.
What does Axon do?
It provides a lot of the plumbing, infrastructure for handling commands, dispatching events, managing the state aggregates on the right side, coordinating sagas. It handles a lot of the boilerplate complexity.
Got it. And what about storing the events themselves? We need something good at handling immutable, ordered logs, right? Not just a standard relational database.
That's a great point. While you can sometimes use traditional databases, specialized event stores are often more efficient. We saw mentions of things like KurrentDB.
KurrentDB?
Yeah, it's designed specifically for storing those ordered, immutable event streams. It makes managing and querying the event log itself much easier than trying to shoehorn it into, say, a relational model. You want something that respects the time series nature of events.
Makes sense. And what about cloud-native or serverless approaches? How does this fit in there?
The cloud providers have really embraced these patterns. A common approach mentioned involves using something like Azure Cosmos DB.
How does Cosmos DB fit in?
Well, Cosmos DB is quite flexible. It can be used effectively both for storing the event stream itself and also for hosting those denormalized read models, perhaps as JSON documents.
Okay, so one database service for potentially both sides.
Potentially, yes. And you couple that with something like Azure Functions.
The serverless compute part.
Exactly. The Azure Functions can act as the event handlers. They listen to the event stream coming out of the write model, process the events, and asynchronously update the various read models stored perhaps in another part of Cosmos DB or somewhere else entirely.
So the functions handle the asynchronous coordination without needing dedicated servers running constantly.
Precisely. It can be a very elegant, scalable, and cost-effective way to build out the CQRS communication layer.
Excellent. Okay, so let's try and bring this all together for everyone listening.
Yeah.
CQRS, it's not about just swapping databases. It's a strategic architectural choice.
Right.
It's about managing system scale by deliberately separating the needs of writing data, which prioritize consistency and integrity, from the needs of reading data, where speed is often paramount.
Couldn't have said it better.
And when you combine it with event sourcing, you get this pathway to building really resilient, highly scalable systems. But
You have to consciously manage that trade-off around eventual consistency. It requires careful design.
it really shifts how you think about data interaction, doesn't it?
It absolutely does. You move complexity, perhaps, from complex database queries and constraints into the application layer, into managing this distributed asynchronous flow.
Making a deliberate trade for user experience in high-volume scenarios.
Exactly. It's fundamental for many complex high-performance systems operating at internet scale today.
So let's wrap up with a final thought for you, the listener, to mull over. We've talked about the technical complexity, managing two models, dealing with eventual consistency, the specialized tooling. Given that an organization adopting this needs to manage these distinct systems and deal with that slight delay in data propagation, what are the organizational implications? What changes in team structure or engineering mindset are needed to successfully operate a system built on eventual consistency, especially when different teams or different parts of the business might be looking at slightly different versions of the truth at any given moment?
That's a really interesting angle. How does the organization itself adapt?
Something to think about as you continue your own deep dive into system architecture.